want to say a few things before we get going. First, thank you to everyone that's participating in this session. This is one of 8 sessions that we're putting on this week to provide some education to our clients, the engineering community in New England, end users, contractors. This went out to all of Buckley's clients, and it was very well received. So thank you for participating. What you're going to see this morning is a condensed version of what we call our advanced lab controls workshop. It's a 3-day workshop that we've developed, Buckley has developed alongside Price, Antec, and Greenheck. And one thing to note there with the Greenheck portion of this, we also are doing Greenheck portions of these seminars. It's another 1.5-hour session. If you didn't sign up for it and are interested in that portion of the seminar, these 2 1.5-hour webinars kind of go hand in hand together. So we're offering 4 Antec seminars and 4 Greenheck seminars as part of this week. We've had over 100 people sign up for this. The person who's going to be presenting this morning is Dave Enns. He's with the Antec Controls Group at Price. And again, this is going to be a condensed version of what we would offer down at Price in their Atlanta facility. So if you want to, if this stuff interests you and you want to go down and get your hands on it and do a 3-day in-depth workshop relative to Antec, relative to Greenheck, and also as part of that, we talk about chilled beams in lab spaces. We talk about air distribution for critical environments, and we get to put our hands on some of this stuff as well. So it's a really good 3 days. It's well spent, and if you like what you see here, please reach out and let someone at Buckley know that you're interested in going to the full thing at Price. And with that, I'll hand it over to Dave and let him get going.
Thank you, sir. Everybody, I hope you can hear me well. If you can't, let us know along the way. I don't want anybody dropping out here. That's one of the joys of doing things virtually like this, but we'll try to take care of that along the way. So I've entered a comment there in the chat section on GoToMeeting. If you can see it, if you have questions, please ask them along the way. I'll try to pause when I see those and get to the questions. So don't feel like you have to keep those just until the end. We'll try to make this a little bit more interactive and hopefully a little bit more engaging. So like Dean said, this is a condensed, and we're going to cover a lot of ground. We're going to start with airflow control devices and the 3 devices that are out there and kind of how we use them. We're going to open up open loop versus closed loop controls and when and where and why we would use them. And then we're going to start to apply them to equipment, mainly in laboratories. So constant volume, 2-position, and VAV style devices and why and where we would use them. That's going to bring up a conversation on speed of response and all of the many definitions of it. Then we're going to jump into humid controls. And finally, we are going to wrap this all up with room control strategies. In the end, most of what we do here is based around point number 6. It's room controls. But we really have to build that whole picture up, starting from the mechanical air devices, moving all the way through equipment, and finally wrapping it up in that last bundle of a room control strategy. So that's where we're going to end today. Again, along the way, please ask us questions as you guys need. Well, let's start with the air valves. I mentioned we're going to split these into 3 groups. Those are VAV boxes that you can see on the top, Venturi valves, like you can see on the bottom image, and the high accuracy terminal, which is a bit of a hybrid between the 2 that you can see in the middle image. All 3 types of devices exist. They all work in their own way, but they all have some pros and cons and benefits and things like that. And really, mechanically speaking, they all just operate a bit differently, which lends them to certain applications better. But as far as mechanical operation, the performance and flow ranges, the accuracies and things like that, they do all vary a little bit. For those of you who are just joining us, feel free to ask us questions along the way using the chat function. What we like to do is take these three styles of devices and group them into two different groups. Those that are mechanically pressure dependent and those that are mechanically pressure independent. So in the first group, the dependent type, are VAV boxes and high accuracy terminals. These two types of devices are really substantially similar, if not frankly identical. And with a type of device like this, and we'll dig more into them, they measure airflow. Pressure and airflow are going to be intimately tied together. They're essentially the same value. So mechanically speaking, these devices are pressure dependent. Across a line in the sand is the Venturi valve. Mechanically speaking, it's completely independent of pressure. Airflow and pressure in that device are in no way, shape, or form linked together. So let's start here with the most simple of the three devices. You've all seen a million of these and applied a million of these things. It's an extremely simple device, the VAV box. A VAV box is just a damper with a method of measuring airflow. The VAV box, however, was never asked or intended or designed to be the most accurate device in the world. They were originally intended and are still used today to be airflow and temperature and comfort control devices, really. So they can measure airflow and they can do an okay job of it, but they're not going to be claiming an accuracy of 2 or 3 or 5% accuracy, really in any sort of range. You may be able to take a VAV box and balance it a certain constant volume airflow and make it a fairly accurate device. But as soon as you try to get some turn down out of a device like this, your accuracy is kind of going to fall off and away. The upside to a VAV box is they're extremely low cost and they use almost no pressure to measure that airflow. So you're going to see a VAV box measure in the 100th to a 10th of an inch kind of range, which is extremely low pressure. Great part of that is they'll work in retrofit applications, they work in low pressure systems, but again, they're not the most accurate and don't have the highest turn down. I mentioned 6 to 1 here. More commonly, you're going to see these as 3 to 4 to 1 turn down ratio devices. So if you're looking at an operating room that needs to go from 25 air changes down to 6 or 10, this device will really struggle to do that accurately. The other devices we're going to talk about can achieve that fairly easily. Really, with the VAV box, one of the defining features, however, is the invasive airflow measurement. So you can see the multi-point sensor we show here. The airflow is directly being captured by that multi-point sensor. It's facing right into the airstream, looking right in the face of it. So any lint or dust or dirt or Kleenex or cardboard or plastic bags or anything in that ducting system can be captured by that multi-point sensor and unfortunately make it not do its job very well at all. In a critical application, that's extremely important that that doesn't happen. And a lot of times we're dealing with dirty applications here. So if you look at an isolation room or operating room, these are very linty and dusty places in the exhaust and return side of the system, and that multi-point sensor can become clogged up fairly quickly. Extremely similar to a VAV box is a technology we call a high accuracy terminal. The high accuracy terminal, for all intents and purposes, is a VAV box. It's just a better VAV box. What it does is measures a higher pressure drop through the device, giving it a little bit more accuracy and a little bit more repeatable accuracy. So a high accuracy terminal, we'll show you one example here. This is the Antec Controls version. Our product name would be the VFX. What we do here is we compress airflow down through that Venturi section. That speeds the air up and creates a pressure drop between that pressure port in the front and the pressure port in the neck of the valve. Now the pressure drop that we're going to see there is orders of magnitude larger than what a VAV box will see. So if a VAV box is measuring about a 1/10 of an inch of pressure drop to achieve its full flow, between those two posts, we're going to see almost 2 inches of pressure drop that we're able to measure using a slightly better transducer. Now there is regain in the aft portion of the valve, so the total drop across a high accuracy terminal is about 0.3 inches. So it's still a bit higher than a VAV box, but it's not that full 2 inches that the sensor needs to see. There's a simple fact when you're measuring pressure. That to a point, really, measuring larger pressures is easier than measuring small pressures. Measuring in the mid span or the top end of the span of a pressure transducer makes the transducer much better at its job. Trying to measure right down to the minimum of what your transducer or sensor can do is extremely tough and not the most accurate thing in the world. So that's why we amplify that pressure drop through a high accuracy terminal. And we do pay a bit of a penalty on the horsepower at your fan, but we get much higher accuracy. What kind of accuracy? 5%. So with a VAV box, no manufacturer, when you combine all of the bits and pieces together, will claim an accuracy from minimum flow to maximum flow. With high accuracy terminals, you can get plus or minus 5% accuracy from minimum to maximum flows. So in these critical spaces like labs, ORs, isolation rooms, and compounding pharmacies, you can really readily apply this product pretty much anywhere and get the accuracy you need to pressurize your room as you intend. So these two devices, like I said, are kind of grouped together. They're very, very similar. And they're similar because they measure airflow. In a device like this, as pressure rises, airflow will rise. Pressure and airflow are essentially the same thing inside a VAV box or high accuracy terminal. They are intimately linked and tied together. So we call these pressure dependent devices. Through the use of electronics and controls, really by having a brain, we can create pressure independence. However, we call that electronic pressure independence or controlled pressure independence. So these devices, no matter how you use them or apply them, always come with a full suite box on top. There's always a controller, transducer, actuator. There's always that full set of equipment to do all of this work. That brings us to the slightly more complicated unit in the Venturi valve. Now, the VV style device is a complete shift in mindset when measuring and metering airflow. The first thing to remember about a Venturi valve is it does not measure airflow, not in any way, shape, or form. It doesn't measure flow. There are pressure taps on a Venturi valve. You may be able to see them just in the top end of that valve, poking into the valve there. If you measure pressure drop across a Venturi valve, you still know nothing about the airflow through that device. Pressure and airflow are in no way, shape, or form mathematically or scientifically linked together. They just aren't. It's not something the manufacturer is keeping from you. They're just not linked. What are linked are the airflow through the device and the position of that internal assembly. So if you'd like more airflow through a Venturi valve, you can adjust what we call the lever arm there on the left, and you can open that valve up a little bit. As you open it up, that position is measured, and it's directly related to an airflow through the device. That airflow is mapped for the whole device from minimum to maximum. Every single Venturi valve needs to be tested to understand what that position versus airflow curve actually looks like. So really what we're looking at are two separate mechanical systems in a Venturi valve. The lever arm and actuator shaft control your airflow volume, and the spring and cone assembly, you can see the cone being pointed to there, are what meter your pressure. So your pressure and airflow are two separate mechanical systems. For the cone assembly, inside of it is housed a highly engineered spring. As the pressure through the device increases, that cone is going to be pushed farther back into the valve. What you can see there, because of that Venturi shape of the outer valve, the orifice where the actual airflow can go through will shrink. The key to a Venturi valve is balancing how hard the spring pushes back with the size of that airflow area. And basically what you can do here is create true constant volume, meaning without the use of controls or electronics or any sort of brain, through the use of a mechanical system, a force balance really, you can meter that airflow perfectly well and just as accurately as a high accuracy terminal. So still good to plus or minus 5%, but that's without using any sort of controls or electronics. The controls and electronics come in when you'd like to select a different airflow. So if you'd like to go from 500 CFM to 1000, that's when your controller kicks in. But your controller doesn't have to do any sort of work if you'd like to always maintain 500 CFM, but your pressure in your system is changing. We're going to come back to that talk when we start to talk about constant volume and how we can apply it to equipment in laboratories and things like that. So how do these devices actually line up as far as pressure and airflow and performance goes? Again, for a terminal unit, there's no claimed accuracy for these devices. You might see from some manufacturers that their transducer has a certain accuracy, or their box has a certain accuracy, or the sensor that captures that airflow has an accuracy. But when you build these all together, nobody's going to claim any one set accuracy for these devices. So we really can't give you that number, but we can tell you the minimum pressure drop you need to push airflow through that device. So we have to read these charts in a certain specific way. I'll always refer to the size 8 box here just to keep it comparing apples to apples. On a size 8 VAV box, you can get about 800 CFM through it. The minimum would be about 160, giving you a turn down of 5:1. To get 800 CFM out of a size 8 box, you need 0.01 inches of pressure to push that air through the device. Now you have to remember how a manufacturer tests these devices. We get to open the damper wide open and take as much pressure out of the system as we can, and then test what this looks like. So that 0.01 is a minimum. If you have that pressure, you'll get airflow through the valve, but you have no control of it whatsoever. If you'd like to control it, you need to damper that airflow off more, meaning you need to increase that pressure drop. So when you look at this performance chart, really there might be one valve or one VAV box in your entire system operating at that minimum pressure. And it's the one as far away from the fan as you can get. Everything else will operate at a higher pressure drop. Let's look at a high accuracy terminal now. These operate functionally identically. However, they operate a slightly higher pressure. But the way we read the performance is identical. A size 8 can go from 80 to 800, giving a 10:1 turndown ratio. It can do it with a plus or minus 5% accuracy. But to get 800 CFM out of a size 8 box, it needs 0.3 inches of pressure just to push that airflow through. Now remember, regardless of the manufacturer, the style, or shape of the valve, that is a minimum pressure drop. So if you call and say, I have 0.3 inches, can I get 800 CFM through a size 8 box? The true answer is yes. But the more appropriate answer is yes, but you cannot control it. You can measure that flow and you can flow it through your system, but you can't control it. If you'd like to control that flow, you need more pressure. So generally speaking, and this is just a rule of thumb, it's not a hard answer to any of life's questions here, but if you have 0.5 inches, if you have half an inch of pressure across any valve size, you can get anywhere from minimum flow to maximum flow, and you can control that airflow. So I generally recommend about a half an inch of pressure drop is what you should plan for a high accuracy terminal in your system. It'll give you good controllability, or at least some controllability, and a full range of airflows that are available. Now, if you call and say, hey, we have a 1/10 of an inch available, can we use a high accuracy terminal? The answer is yes, but you will not get the full turn down. If you have a 1/10 of an inch on a size 8, you might get 100 or 200 or 300 CFM, but you just can't get that full turn down ratio. That's an important point to remember with a high accuracy terminal. We sometimes call these low pressure Venturi valves. That's not a term I personally like to use because it's a little bit misleading. Yes, these can operate at lower pressure drops, but it comes with a caveat of you won't get the full turn down ratio. Now that brings us to the Venturi valve again here, but we have to read this data differently. I'm going to focus mostly on the right-hand side of the chart here on the medium pressure Venturi valve. Valves, for the record, come in 2 styles, low pressure and medium. The sacrifice you make to go to the low pressure valve is your maximum airflows are lower. So on a size 8 box, instead of going to 700 CFM, it will go up to only 500 CFM. However, it can be operated down to 0.3 inches instead of 0.6. So knowing that, we'll stick to the performance of the medium pressure valve. So we read the first part similar to the others. It can go from 35 to 700 CFM, giving it a 20:1 turn down ratio. We're going to come back to that when we talk about energy a little bit later. It can achieve anywhere from that minimum flow to maximum flow, anywhere between 0.6 inches and 3 inches. So if you have 0.6 inches of pressure drop, you can get 35 CFM through your valve. If you have 0.6 inches, you can also get 700 CFM out of your Venturi valve. okay? So to get 700 CFM out of that valve, you do not need 3 inches. You don't need the maximum pressure to get maximum flow. If you have it, the valve will still work, but you can operate anywhere between minimum pressure and maximum pressure. You really can't operate outside that range at all, however. So if you have 0.5 inches, you don't have enough pressure to push that cone into the place where it's able to do its job. And if you have too much pressure, if you have over 3 inches, you're going to get some stack up. Basically, the spring inside that cone is fully compressed, and instead of being a spring, it's now a cylinder, and it's not able to meter that size orifice anymore. So we have to read this data differently. It's really critical that we do that. Now, when I say that about the Venturi valve, that we have to have that pressure between 0.6 and 3, it's extremely critical. It's so critical that we put a transducer on every single controller we manufacture to measure that pressure drop. Because if you don't have it, the only fix is to go get it. If you only have 0.5 inches, your balancing team says these valves just aren't working, there's no fix within the valve and controls for that. You need to get more pressure to that system. That's the first thing we have technicians check when they start one of these systems up, is do you have pressure drop across your device? If you don't have it, don't start your fume hood or your supply or exhaust up. Don't try to balance or commission these systems. Get the pressure in line first and then do the rest of the work. So instead of just a low pressure switch on every single device, which would tell you whether you have airflow or not, we put a real true transducer on there. So you know if you have just enough pressure or if you have happily 1.5 inches or something like that. What this is going to let you do is fan static reset. So once your system is up and running and it's been built exactly as you designed, you're able to intelligently reset these systems down to save a little bit of horsepower and a little bit of energy. All of that data is available over the building network, and for fume hoods, available right at the fume hood as well. So let's move on a little bit here to the valve construction. You all know probably more than I do about VAV box and their construction, so we're going to leave them out here. But for high accuracy terminals and Venturi valve, they are generally always aluminum bodies. They're always a spun aluminum body. Some of the hardware internal to the valve, so that shaft assembly you see internal and some of the mounting hardware, that will be stainless steel. And the internal center shaft will be a Teflon coating. Teflon is extremely smooth and it's a great bearing surface, and that's why it's actually used here. For any clean air application, so almost all supply valves and most, if not all, general exhaust valves in the world should be aluminum. It's inexpensive to make compared to stainless steel. It's lightweight and it's easy to manufacture. Where you need chemical resistance with a Venturi valve, instead of going with a stainless steel valve, which would be costly to buy the sheet metal, costly to spin, expensive to hang, expensive and heavy to mount, you should go with a phenolic coating. It's much, much more cost effective, to the point where most manufacturers don't spin a stainless steel valve. It's really just not cost effective. In the most commonly used coated valve, we call it a class 1 valve, there are still, however, some stainless steel components. So you can see some of the mounting assemblies are still stainless steel, and some of the hardware is still stainless inside of that valve. Phenolic and stainless cover very similar spectrums of chemicals that they're resistant to. I would say 95% of fume hood valves we ship out are coated in this class 1 coating. The next nearly 5%, however, are this class 2 coating. In a class 2 coating, we find that a phenolic coating covers an even broader spectrum actually than stainless steel does. So in this style of coating, we're going to coat every metallic part with either Teflon or phenolic. In this style of valve, the Teflon goes from PTFE to PFA, which is slightly more costly, but it covers a bigger, better spectrum of chemicals that it's resistant to. So if you're dealing with the chloric acids, bromine, there's a couple examples up there, that's when the class 2 device is going to be required. Some systems, however, will need the highest level of corrosion or chemical resistance. We call that Kynar coating, or PVDF. In this device, all metallic parts are coated in either PFA Teflon or Kynar. This coating is monstrously expensive. On an 8-inch valve, the coating will cost more than the valve and controller combined. But what you're going to get is extremely broad spectrum, high level chemical resistance. So there are certain things where your only option is a Kynar coating. We keep a full list up to date on these coatings. So if you have questions about what chemicals are being used and what coating to apply, we can help with that. We don't know the full list off the top of our head because there's thousands and thousands of them, but do lean on us if you have a question about what to use where. So let's move on from the valves over to open loop versus closed loop devices. We grouped the valves into mechanically pressure dependent and mechanically pressure independent. And really what we were introducing is closed loop versus open loop controls. So in a high accuracy terminal in a VAV box, we're doing what's called closed loop control. Again, we measure airflow, which also happens to be our controlled variable. We measure airflow and move a damper to control that airflow. We measure and move over and over and over again. This is a closed loop style of control. There are, however, quite a few different ways to do that. You can measure velocity pressure, which is what your typical VAV box will do. You can do it with a pitot tube, you can do it with an orifice ring, flow cross, lots of things like that. You can use vortex shedding. There are some high accuracy terminals that use vortex shedding, which is a fairly interesting phenomenon where basically you count pulses in the airstream that are caused by obstructions. So you see this really in any moving fluid. You can use thermal dispersion, which is basically the measuring of a drifting heat energy. So if you heat the airstream up and measure how far away that heat drifts, that's called thermal dispersion. It's an extremely accurate way of measuring airflow, actually. The other way you can do it is measuring static pressure. I'll show an image of that because that's what we do inside our VFX as well. So those pressure posts you see in the airstream are actually measuring static pressure. Again, static pressure is directly related to airflow. You can see the equation we use on the right there. It's a very common one used for measuring and calculating airflow. Whereas if you measure the pressure and you know the constant for the valve, which is just a tested variable, you can calculate the airflow. Or vice versa. If you know the airflow and you know the constant, you can back calculate the pressure across the device. For the static pressure, one of the reasons we really like that method of measurement is it brings the pressure measuring posts or orifice, to the back side of the valve, meaning it's out of the airstream. Air is going to flow into the post and around and away from that opening, meaning it's a little less susceptible to contamination. Now, for contamination, anytime you measure airflow, whether it's using velocity pressure or static or vortex shedding or some other method of measurement, no matter how you do it, if you measure airflow, you are susceptible to contamination.
That's
Sorry, was there a question there?
No, I'm sorry, I coughed.
No problem at all. So with any method of measurement, you are susceptible to contamination. To give an extreme example, if you were to take a Kleenex inside the high accuracy terminal you see here and wrap it around that post, it would no longer measure airflow very well at all, if at all. Any method of measurement is susceptible to this. So all measuring valves may need to be inspected and may need to be cleaned. Some styles are more resistant to measurement, but they are all susceptible to contamination. Oops. Another thing we're going to have to consider is the flow control characteristic of a closed loop valve or of a mechanically pressure dependent valve. All of these devices basically use some sort of damper, whether it's a pose blade or a butterfly or two dampers or one, doesn't matter. They all suffer from an opening characteristic. Basically, at one point in time, they're closed, and at one more step open, there is now some airflow. So you go from 0 to something. No controllability exists between 0 and that next value. You're either at nothing or that value. So there's no resolution, there's no control. We call that quick opening or crack open is what I like to call it. You see it on a garden hose all the time. You open and open and open and you see nothing until you see 20 gallons a minute coming out of your faucet. VAV boxes and closed loop style of valves do suffer from this as well. That's why we like to get them into that much more linear opening area. Basically 25 to about 75% open, and that's highly dependent on your system, highly dependent on the box type and shape and size. But you basically want to be in that middle range to give you more linear better, more accurate control. Something to consider here, as well as, again, pressure and airflow are directly linked together. So consider a manifolded system, whether these are fume hoods or operating rooms or whatever it is. Say you have 3 closed loop valves, all flowing 700 CFM through them. If you damper off one of those valves, so imagine closing a fume hood and you close it down to 200 CFM. What's going to instantaneously happen, because the pressure in this system will have risen, is that the airflow in the other valve. We're getting a little bit of feedback. Sorry guys, if you guys aren't all muted, if you don't mind muting yourself, I'm hearing a little bit of feedback, but we'll keep going here. So what's going to happen in this system is we're going to instantaneously increase the pressure in this system and the flow through the other 2 valves. So if you imagine fume hoods, your middle fume hood's still operating as intended, but the other 2 fume hoods instantaneously and momentarily have increased their flow rate, which is an unintended consequence. The other 2 valves will have controllers that will take care of this, and they can take care of it fairly quickly and accurately, but still for a few seconds they are not at the airflow they want to be at. And all of this occurs because pressure and airflow are directly linked together. Now that brings us to open loop controls. This is the style we use for a Venturi valve. We call it open loop because we don't directly measure the variable we are trying to control. In a Venturi valve, the value we're trying to control is airflow, but the value we measure is position. So there's no direct feedback of that measured value. We still have an understanding of what airflow we're at, and we can still measure and control it, but there's no direct link. Now, the great thing about these, number one, because they're not naturally shut-off devices, but also because there's no measurement happening in between these and there's no resolution to deal with, there's a stable opening characteristic. So from minimum flow to maximum, you get nice, clean, fairly linear, stable opening on a Venturi valve, which gives us that huge turn-down ratio of 20:1 in some Venturi valves in the medium pressure variety. So this is really nice if you're dealing with fume hoods or even low flow applications. If you really need that low flow and high controllability, the Venturi valve is going to be a little bit better at that. Now that being said, creating a Venturi valve is a whole lot harder than creating a closed loop style of valve. Every single Venturi valve needs to be tested. Every single one needs to be put on a highly calibrated rig and run through its paces of what position is equal to what airflow. So basically the airflow rig will push some air through it and measure that itself and then record the position the Venturi valve's at. That's a 48-point test. Automated and working properly, that takes 12 to 15 minutes per Venturi valve, so long as no part fails or it's not out of calibration or something like that. So it's a highly labor-intensive portion of the Venturi valve creation is this test. At Antec, we have 3 of these rigs running full-time to do this kind of work that are validated and accredited using by the NAVLAP organization, pardon me. So NAVLAP is the National Voluntary Laboratory Accreditation Program. Basically what they've done is a third party has come into the factory and said the accuracies we claim to test to and we claim for the valves, we are capable of actually producing in the laboratory. So what we have is a laboratory accredited by NAVLAP, but not Venturi valves accredited by NAVLAP. There's a bit of a misconception in the field that Venturi valves are NAVLAP certified or accredited, where NAVLAP doesn't accredit Venturi valves, they accredit laboratories that do this work. Now, for the Venturi valve, consider that same application. And basically what we're doing here is comparing open loop versus closed loop controls. Say you have those 3 fume hoods hooked up to the same manifold again, and you go and you close that middle fume hood down. What's going to happen again is instantaneously your system pressure will increase. However, the other 2 valves in that system will not change airflow whatsoever. The spring and cone assembly will automatically, mechanically, naturally take up that change in pressure, and they'll do it instantaneously. No controller had to be involved whatsoever because pressure and airflow are mechanically not linked together. So that's the fundamental difference between open loop and closed loop controls. is really this application right here. So how can we start to apply what we know about valves now to laboratories and equipment? So what we're going to break this down into is constant volume versus two position versus VAV. Now we'll start with high accuracy terminals and terminal units. All of them are VAV boxes. They are all variable air volume boxes. We sometimes see on schedules that a terminal unit can be called a CAV, or constant air valve, something like that. That's a bit of a misdirection. If you take a VAV box or a high accuracy terminal and control it and hold it to a constant volume, we call it a constant volume device. However, the equipment we need to do that is still full VAV. It's a controller, an actuator, and a transducer doing all of that work of maintaining a constant volume. So we call that controlled constant volume. So this is where we have to separate closed loop valves and open loop valves. With a high accuracy terminal or VAV box, you can achieve controlled constant volumes. However, on a Venturi valve, on an open loop device, we can achieve mechanical constant volume. So I'll show an image on the next slide right away here. But if you take all of the controls and electronics off and you physically fasten that valve into place, so you test it and you set it up for 500 CFM and you lock that into place, without the use of electronics, you can maintain that set 500 CFM. So if you have a biological safety cabinet in a compounding pharmacy, or you have a fume hood that's constant volume in a laboratory, or even an extremely simple retrofitted space that just needs to maintain a set flow, it needs to be quick and dirty, you can use a mechanically set constant volume device in that space. Now, the reason we recommend that is it's lower cost than a VAV box. Number one, the capital cost is lower, but number two, the maintenance cost is lower because there's no parts that are moving, there's no controls, electronics, or motors of any kind. It's just mechanically fastened into place. So this is where, for you engineers that are speccing Venturi valves and scheduling valves, it's important to note the difference. We see a lot of schedules that call out constant volume airflows on Venturi valves, but what they would like to see is a controlled constant volume. You want a full sweep valve, you just don't want it to move. You may want it to move in the future or reset the set points, but that's a controlled constant volume. If you want a true mechanically set constant volume device with a Venturi valve, it's important to note that on schedules and in specs to use a mechanically set Venturi valve. So let's move on here to two-position control. It's a fairly similar conversation. For a VAV box or high accuracy terminal, you can achieve two-position control. You can control to a minimum flow and a maximum flow. However, that's still a full VAV box that's just controlled to two different set points. So the equipment required and the capital cost is identical. With a Venturi valve, however, for anybody wondering, that's Siri on my Apple Watch, so we'll move her away for a moment here. On a Venturi valve, we can achieve mechanical two-position, meaning using a lower cost actuator and a set of relays, you can drive to a minimum position to a maximum position. Nothing exists in between those two settings. So if you're at 100 CFM at the minimum, you could flip a switch and drive open to 500 CFM, for example. You cannot achieve 400 without mechanically changing something about that actuator and its hard stops. So if you're looking for a set of snorkels or a canopy hood, or even a two-position fume hood or something like that, the two-position valve can be well applied. It doesn't need the full VAV control and monitor on top, but it can still achieve two different set points. The last one we'll talk about here is the full VAV control. For both devices, whether it's a high accuracy terminal or a Venturi valve, the equipment is extremely similar. You need a controller, you need an actuator, and in some cases you need the transducer to measure that flow, and you can achieve anywhere from minimum to maximum flow on that box. So how can we apply these devices? My recommendation is you should always strive to use a constant volume Venturi valve. That's a bit of a blanket statement, but I do stand behind it. If you have true constant volume and you know it's going to maybe change once in its lifetime, meaning 5 years down the road, you might change the flow by 100 or 200 CFM, for example, try to use a constant volume Venturi valve. It's the least expensive, the least complex, and the easiest to set up. The maintenance is the lowest, and it will still provide you stable and accurate control all of the time. This is the best solution for a lot of applications. One thing you should consider adding to that constant volume venturi valve, however, is a pressure switch. The pressure switch will be an air proving switch. So basically, when your system sees the pressure switch contact closed, it knows airflow is present. And when it sees it open, it knows airflow is not present. So it's, do I have this airflow or not at all? It's a nice monitor for that system. If you're using a high accuracy terminal for equipment control, so thinking, biological safety cabinet, snorkels, things like that, I do not mean fume hoods, you should consider using standard speed actuators whenever possible. Remember, a high accuracy terminal is a closed loop device. It is always measuring and controlling. Measurement and control is always easier to do at a slow speed. Regardless of the manufacturer or the type of device, it's easier to do when it's slower. So in an operating room or an isolation room or even a compounding pharmacy, if you can use standard speed actuation, you should. The motor costs a bit less, and it's easier to set up and tune and can be more accurate. An operating room, for an example, or even an isolation room, for example, might go from a minimum set point to a maximum in setback modes and occupied modes. That change does not need to happen in the matter of a few seconds. It can take maybe a minute. The room is still changing over quick enough for its usage, and we don't need to incur the cost and complexity of high-speed actuators for that. Anytime you increase the speed of a measurement and control system, you increase its complexity and increase the cost to set it up and tune it. Now, when fume hoods are present, essentially all devices in the space should be high speed. So the fume hood itself, number one, whether it's a VAV box, high accuracy terminal, or venturi valve, it should be high speed. The supply and general exhaust, they should also be high speed. And even the equipment, you should probably consider using high speed actuation. So if you have supply, exhaust, and a fume hood, and you add in a snorkel that's 2-position, for example, that should likely be a high-speed device as well, just so that everything tracks at the same speed. Now, that brings us to a really interesting part of the conversation about speed of response. Unfortunately, speed of response has become a bit of a marketing tool amongst manufacturers. If you want something to sound good and sound like it's a high quality lab grade device, a lot of times you'll hear it described as a high speed device or a quick acting or a quick speed of response device. However, a lot of times you won't see a definition for speed of response. What does high speed mean? I've personally broken these down into 5 different definitions. So these are my definitions. You're not going to find these in an ASHRAE journal. So you might have different ones for yourself, which is perfectly fine. But I've broken this down 5 ways. The first and most simple way is actuator speed, or full stroke time. So if you take a Belimo actuator and look at its cut sheet, it will tell you the full stroke time. So from minimum to maximum, how long does it take this actuator to move? A standard speed Belimo takes about 90 seconds. A high speed Belimo takes 4 seconds or less. Simple fact. Now, this doesn't tell you the whole picture. It tells you actually a very small part of the picture. If you say, how long will it take to perform a certain action? The actuator speed will tell you generally what the range will be, but that's all it's going to tell you. If you need to make a minor change from 500 CFM to 510, you might get the same total response time out of a standard speed actuator and a high speed actuator. Even though one is moving much quicker than the other, the minute change it needs to make can be accomplished in a single step, essentially. The next definition is the speed of response to a change in duct static pressure. So we actually introduced this comment earlier on when we talked about 3 fume hoods manifolded together. When you look at high accuracy terminals and VAV boxes, with high speed actuation and high speed controls, they can move very, very quickly. So when your duct static pressure changes, whether it's a small change or a large change, we can accommodate that change quickly. Quickly usually means a second to 2 or even 3 seconds. However, for a venturi valve, that change can happen instantaneously or nearly instantaneously. It because there's no actuator involved in the system whatsoever and no controller at all, that change in duct pressure will be taken up mechanically and instantly. So this is where the Venturi valve starts to shine a little bit, specifically in fume hood applications where you'll see rapid and large changes to your duct pressure. The Venturi valve will handle that application better. VAV boxes and high accuracy terminals can still do the work. High accuracy terminal will do it better because it is more accurate, but they will be a little bit worse than the Venturi valve. The next type of speed of response is the speed of response of a space after a change is introduced. So in the lab environment, ANSI Z9.5 actually gives us a number for this, and it's 10 seconds. From the time you make a change, so whether you open and close a door or open and close a fume hood, for example, your room has 10 seconds or less to get back to the proper pressurization. 10 seconds is basically an eternity in this world, and usually that can happen between 2 to 4 seconds with most control systems. However, it is understood for most laboratory spaces that when you open a door or when you change fume hood position, laboratory pressurization is momentarily lost or changed. So when you open a fume hood and introduce more exhaust air, you temporarily make the room more negative, which is usually okay. When you close that fume hood, you may cross the threshold to neutral or even positive pressure as you decrease the exhaust flow very, very quickly. In most lab spaces, that's actually okay. If you're dealing with high containment spaces, meaning above BSL2 or even some BSL2 style spaces, that becomes unacceptable. So for the 50 BSL4 laboratories in the world, they can never go neutral. They cannot go positive. They always need to be negative. This does not become a matter of speed, becomes a matter of balancing the room out. Meaning, is your offset and air change rate capable of always staying negative? And is the usage of your fume hoods capable of always keeping the room negative? Basically, is the airflow balance ever going to go positive? And if it is, we need to change the setup of that space. The next type is speed of response to a control signal, or we might call this controlled response time. So if you look at a closed loop style of device, it needs to sample the airstream, compare that sample to the set point, calculate where it would like to go, it needs to go there, and then it needs to resample and repeat. This can happen at a very, very high speed, but it still takes time. No matter how fast processors and controllers get, this will still take some time. If you make only a closed loop device, so if you're a manufacturer of only closed loop styles of devices, you need to make those closed loop style of device look like a Venturi valve. Remember, Venturi valves can be advertised as instantaneous speeds of response due to that second definition we gave. So if you need to make a high accuracy terminal compete with that, what you can say is they have a high speed of response to a control signal. Meaning, if you look between point number 3 and point number 4, from the time you calculate where to go and from the time you start to go there, controllers can do that portion of this calculation very, very quickly. It can happen nearly instantly in much less than a second. So for high accuracy terminals, they do have a high speed of response to that control signal. They start to move very, very quickly. What this number doesn't tell you is how long does it take them to complete the movement. If I need to go from 500 to 1,000 CFM, I don't really care how long it takes me to start going towards 1,000. I care how long it takes me to go from 500 to 1,000. That might be a couple of seconds. That's the number I need to know. But I might start to move that way in a matter or of a fraction of a second. So one of these values, the total controlled response time, is a useful thing for us to know. The other is completely meaningless. So this is where you shouldn't ever get caught up in the language used of talking about these speeds of response. It's important to compare the devices. In some aspects, a Venturi valve can be faster than a high accuracy terminal, but the most important thing here is if we do care about speed, we need to define the speed. If you need a device that controls or accommodates a change in duct static pressure instantly, you need to define that and then select a Venturi valve. If you need a device that can accommodate a duct pressure change in a matter of 3 seconds or less, that's okay, but we need to define it and then compare device to device. A high accuracy terminal may be able to do that for you. The last type of speed of response is about the fume hoods. We're not going to dig too much into this today. It can be its own conversation that lasts about an hour on its own. But really what we're measuring here is from the time we introduce a change in sash position, how long does it take us to get back to the required airflow? So from the time I start opening the sash or the time I stop opening the sash, how long does it take me to get to the required airflow? Generally speaking, there are 3 ways to do that. You can start at the start of sash movement, you can start basically in the middle of the sash movement, or you can start at the end of your sash movement. This is important to define because your sash does take a second or 2 to open. You can open them at a rate of about 1.5 feet per second. The commonly accepted time that is okay is 3 seconds or less. We're going to dig into this a little bit more when we get now into fume hoods. Now, fume hoods are really what make a lab a lab. They're what make wet labs a little bit complicated. And this is what's going to drive you to a certain style of valve over the other, because fume hoods are really the most important piece of equipment in a laboratory, oftentimes. Fume hoods are what we call the primary engineering control, meaning if the fume hood is doing its job and it's being used properly by the user, we should be doing a pretty good job of containment in that space. But fume hoods come in a lot of different shapes and sizes, whether it's constant or variable volume, low flow, floor mounted, or perchloric. There's a lot of different types. All of these types are actually defined in the ASHRAE handbook from 2019, and that book does give a fairly good definition of each type. I want to dig into constant variable volume and perchloric for a few seconds here. There are about 750,000 fume hoods in the United States, 750,000 fume hoods in the United States. About 1/3 of those are constant volume. Now that number is debatable, it is a bit of an estimate, but the point is constant volume fume hoods are not an old technology. They are still a viable fume hood to use and a good design to use sometimes, but they're not always applicable. For a constant volume fume hood, they maintain an approximately constant volume face velocity, but the sash of these hoods can move. So the containment's pretty good on a device like this. Essentially what's going to happen is there's going to be an open bypass. So on this hood, you can see the louver system on the front of it. On some fume hoods, that open bypass will be in the top of the fume hood or the sides of the hood. They come in a few different shapes and sizes. But what you're going to do is as the sash opens, we're going to proportionally close that open bypass. And we're always going to exhaust a set constant volume amount of air. This is a good application for a mechanically set constant volume Venturi valve, just by the way. Constant volume fume hoods should be used when they don't inflate your makeup air number. So for example, if you have a thermally driven or a ventilation driven laboratory, you should probably use a constant volume fume hood. So for example, if we need 1,000 CFM of supply and 1,100 CFM of exhaust to make the room negative, and my fume hood at maximum only consumes 500 CFM, that's a great way to use a constant volume fume hood. Opening and closing that sash will save you nothing for energy because we already needed to make that air up for ventilation or thermal demand. Any time that your fume hood, when it's open, will increase your makeup air number. So if your air change rate is 6, for example, and your thermal load is extremely low, and if when your fume hood opens, they would consume 2,000 CFM, but you only needed 1,100, that is a good reason to use a variable volume fume hood, which we'll introduce here. So with a VAV hood, we'll skip past the text and just show the image here. Basically, there's no open bypass. There may be a small restricted bypass to always ensure some air flows into the hood, but it's not a big open bypass. So as the sash opens, we need to provide proportionally more airflow. On a variable volume fume hood, we can drive down on some of these hoods down all the way down to 85 CFM. So on a 4-foot wide fume hood, according to ANSI Z9.5, so long as containment is being maintained, we can get down to 80 or even 85 CFM on these devices, which is much, much lower than the 400, 500, or even 600 CFM they'll need in the open position. So VAV fume hoods are a really simple way to increase your energy savings sometimes. Now I want to introduce here, kind of as an aside, the perchloric acid hood. I don't know if you noticed earlier, but when we were presenting the Kynar coating for Venturi valves, there was a spot at the bottom of the screen that was blank. We used to list perchloric acid as one of the things the Kynar coating can survive. Now this is true. A PVDF or Kynar coating can survive in a perchloric acid environment. The acid will not harm that Kynar coating. However, perchloric acid is its own special beast in the lab environment. Perchloric is an extremely active oxidizing agent. Now, when perchloric acid dries, it forms something called perchlorate. Perchlorate is essentially a bomb. When exposed to certain elements in the air, it can explode. Perchlorate likes to get into seams and cracks and any small nook and cranny and likes to dry up and form these bombs. Unfortunately, in the lab environment, people have been killed by perchlorate. So for perchloric acid systems, there's two requirements. Number one, we can't have any manifolded system whatsoever. So we'll go from a single hood up to a single fan. The second requirement is they must be seamless. Venturi valves, if you look inside the guts of them, are filled with seams. There are a lot of places that this perchlorate could fill up, and it could get in and could create this explosive element. So this is where we cannot apply airflow control technologies to perchloric systems. So it's not a VAV box or high accuracy terminal or a Venturi valve. None of those can be used in a perchloric system. You need to go directly from the hood straight up to the bypass fan. So that's why we don't show perchloric acid on that Kynar slide anymore. Just to drive this point home a little farther, we've been to the point where we were building Venturi valves for a project, and we saw one in the factory named perchloric acid hood valve, and we held that valve back, and we had to help them redesign that laboratory to make it work, because we cannot put perchloric acid, we cannot put valves, in a perchloric acid environment. Now for all these styles of fume hood, just getting back to the common hoods here, they come in vertical, horizontal, or combination style sashes. In my experience, combination is getting a bit more popular when we look at these hoods. But there are a few types of control we can use for all of these different types of hoods. By far and away, the most common is vertical sash sensing. Vertical sash hoods are still the most common one we see. So in the back of a vertical sash hood, you'll have a counterweight. On the image on the left, that's what's shown in blue. The easiest way to control these hoods is to take a stainless steel drawband cable and mount it to that counterweight. The counterweight will move linearly with the sash, and basically what it will do is measure how much open area we have. Sash sensing is essentially that. We measure the open area. We already know the width of the hood because it's not changing, and we now have measured the height, so we get an open area in square footage. We know if we want to maintain, let's say, 100 feet per minute, that it's really easy to calculate how much airflow will be required to achieve 100 feet per minute. So for example, if you have 10 square feet of open area, it will take 1,000 CFM approximately to achieve 100 feet per minute there. That's all sash sensing is. It's an open loop control strategy for fume hoods. For horizontal hoods and combination hoods, however, that open area is not only affected by the vertical movement of the sash. Specifically for combination hoods, the panes of glass can move to the left and right as well. So your sash may not be engaged, but you can open up a large amount of the open area using the horizontal sash panes. To measure and control these, what we use is a sidewall sensor. This is essentially a pressure sensor that measures essentially the velocity through that threshold. It's a little bit slower than sash sensing. Sash sensing is, by the way, extremely quick. Sidewall sensing is a little bit slower, so instead of a 1 second speed of response, it can achieve a 3 second or less speed of response, but it is a bit more accurate because it's closing the loop for us. It's actually measuring the face velocity. So where sash position sensing is fast, it won't compensate for obstructions. So somebody standing in front of the hood won't affect sash position sensing. It's very fast and very, very stable. Sidewall sensing, on the other hand, is very accurate. Though because it is a control loop, it is tunable, it can overshoot and undershoot a little bit, and it's a little bit slower. What we like to do is called hybrid sensing. So especially for a combination sash, what we think we should do is use both sensors for what they're best at. Sash sensors are quick, so whenever the sash is moving vertically, we would engage our sash position sensor. This gives us a really good first guess. As soon as the sash stops moving, we would give control over to the sidewall sensor, meaning get us close, but then give control to the more accurate device to tweak and tune us right into the place we actually want to be. This is now also a redundant system. So if my sash or sidewall fails, we can still lean on the other sensing element to give us the right, or at least mostly accurate face velocity on that fume hood, which makes sure we don't ever have to shut the fume hood down for the technology that's sensing that face velocity. Hybrid sensing is the most preferred for all of these fume hood technologies because it is the fastest and most accurate system we can offer. Now, before we open the floor up to questions here and before we close out for today, I want to introduce room controls. Now, Antec Controls by Price is a controls manufacturer. The valves are a medium for the controls, but oddly, what we talk about most are the Venturi valves. But the whole entire point of this presentation leads up to how do we control and pressurize a space. Generally speaking, we want air to move from a clean space to a less clean space. To ensure that happens in a certain direction, we are always going to use some sort of offset between all of your supply and all of your exhaust. Now, our goal as design engineers is not to create a system with a certain amount of leakage, with a certain amount of offset to hit a certain pressure. Our job is not to line up all three of those things. Our job as mechanical designers is to ensure we create a mechanical system that is capable of achieving a certain pressurization given a range of leakage rates in my space. Basically giving my balancing and commissioning teams the authority and ability to correctly pressurize these spaces. That is our job as designers. And I say this because you're never going to have a perfect understanding of how tightly sealed your room is. You can get a general idea of room leakage. If you go into an old building on an old campus that's been leaky and it's been leaky for 100 years, you know you're going to need a larger offset than a tightly sealed, brand new constructed high containment lab. But you won't generally know exactly how much leakage you have. So you could look at data like we have here, which is third-party data from 97, that just lines up the open square footage you have versus how much airflow you need to achieve a certain pressure. So for example, if you need 0.01, you know you have a half a square foot of open area, you'll need about 100 to 125 CFM of offset to achieve that. As mechanical designers, we won't have information this good. We'll generally know where on these red curves we sit, but we won't know exactly where. So sometimes we'll see airflow balance plans that show 100 CFM of offset to hit minus 0.01 with an air change rate of 6 air changes. And we'll see that needing to be exactly hit upon. That's in the contract documents, that we must achieve this pressurization at this offset. I'm here to tell you that that's not our job. Our job is to make sure the balancing team has the authority and ability to hit 0.01 inches. That might happen at 1 CFM of offset, that might happen at 1,000 CFM of offset. Designing a mechanical system to give you that range of airflow difference is nearly impossible. But we can provide, let's say, between 50 and 200 CFM of offset to the balance teams to make this happen. That is our job. Now, when we're doing our job, there are two types of pressure control we can use and implement. By far and away, the most common is airflow offset control. You might call this flow tracking or tracking control or volumetric offset. There's 101 names for this that all mean the same thing. Airflow offset control is just simple math. All you do is add up all of your supply, add up all of your exhaust, and make sure there's a distance between them. So in an example I gave earlier, we need 1,000 CFM of supply and 1,100 CFM of exhaust. That's a negatively pressurized room, and we will always maintain minus 100 CFM of offset. Now, this is completely independent of room pressure. This is an open loop control strategy. We know that creates pressure, but we frankly have no idea how much pressure it will create. That will depend on the volume of the room and the leakage rate. In a more tightly sealed room, it will create more pressure. In a leaky room, less pressure. If we leave the doors open, or if we knock a wall down or punch a hole in the wall, it might actually create no pressure whatsoever. But the great thing, and also the downfall of offset control, is that it will not care about that whatsoever. It will maintain that 100 CFM of offset. Maintaining a certain pressurization is up to people. It's up to the human. Through the use of monitoring systems and regular reporting, we can ensure airflow offset control is doing its job. So in most, if not all laboratories, this is the method of control we will use. But it's also very commonly applied with an independent pressure monitor. Generally, a pressure monitor will watch that pressure and alarm over the building network to tell you if a room is inside or outside a certain range of pressures. That's a very good, simple, and accurate way to control these spaces, and it's trendable. The human or even the BMS can trend this data over months and years and just make small tweaks and offsets to that airflow, to make sure we're still at the pressurization we want to be at. Anytime you're doing high-speed control, so really anytime you're in a laboratory environment, this is the method of control you should be using. It's also very, very good in compounding pharmacies and operating rooms. The last thing I'm going to present, however, is pressure control. Pressure control is essentially identical. It uses a difference between supply and exhaust. However, instead of controlling to a CFM offset, it will control directly to a pressure. It won't care what offset it uses. It will hit, let's say, minus 0.01 inches, but it doesn't care if it uses 1 CFM or 101 or 1,000. It will always tweak and tune those airflows to get you the right pressure. Now, the nice thing about this is it's closed loop and more accurate. It's really good in stable environments. So in an isolation room, this is a great control strategy because the doors are generally closed, traffic isn't very high in and out of these spaces, and it gets to do its job very, very often. In a high traffic space like an operating room, when the doors are constantly being opened and closed, pressure control starts to fall apart. It can either be driven wild by the doors, or more appropriately, doors opening and closing would freeze this system, making pressure control really turn into volumetric offset control. In a laboratory environment, specifically with fume hoods, when you're drastically changing the exhaust airflow rate, you're doing it by a large amount and you're doing it often with these fume hoods, pressure control can be driven nuts, meaning it's trying to make these rapid changes to achieve a very accurate small pressure in the space. The fume hoods will just drive it wild all the time. Whenever you're using a high-speed control system, we don't recommend this pressure control. It is possible, the controls are always capable of it, but it is much, much harder to tune and much harder to maintain. The last thing I'll mention here before we open the floor up to questions and complete the presentation is if you'd like to do pressure control, there's 2 things you need to do. Number 1, you need to draw in pressure monitors. If you want to achieve pressure control, you need to measure room pressure. We have seen sequences that call out pressure control, but then specifically disallow room pressure monitors and sensors. There's a bit of an issue there in that if you want to control pressure, you do need to measure it. And the last thing I will say here is no matter which type you pick, it's important to accurately call them out in specifications and sequences, because again, they require different pieces of equipment and they will be set up and tuned and maintained differently. They achieve the same goal, but they do it differently. So with that, I'd really like to thank you all for taking your Monday morning with us here and learning about valves and their controls. My name is David Enns. I've been working with Buckley on this presentation. If you have any questions, my contact information is davide@antechcontrols.com, or you can reach our common inbox at applications@antechcontrols.com. So again, thank you for the time, and I'd like to open the floor up to any questions. If you guys do have them after the fact, please reach out to Dean or Matt, the guys from Buckley. They can help and they can get in contact with us. Doesn't look like there are any questions. So again, thank you for your time and have a great rest of your day.
Thank you.